Okay, here's a problem. So what we want to do is determine the time needed for this value of d to change from 3 down to 0. And so let's kind of classify this. This is a time spanner problem because we know where the blocks are now at time equals 0. D will be 3 and they're at rest. And then after some period of time occurs, D will end up being 0, and what we're asked to find is what time that is. So anyway, it is a time spanner. What that means is we will then find the acceleration or the double dot of something and then integrate it backwards. If the acceleration or double dot term is constant, then of course we're not going to actually integrate. We're going to go use the equations that came out of chapter 12 to do it. The other thing that we're going to do is determine if we need a free body diagram. So we're going to count the degree of freedom, and the degree of freedom is not too bad in this case. Body B can move, and so we would count 1 degree of freedom for body B. If you stop body B, in other words motor D as in dog, you stop that motor, body B will stop, but you can still pull motor C, which means that you can still pull block A. So it's 2 degrees of freedom, which is what we have here. 2 degrees of freedom there. What that means is if I know any 2 double dot terms, I can find all double dot terms. If I know 2 single dot terms, I can find all single dot terms. If I know any 2 positions, I can find any other position. So that's basically what it means. Now, if you look at the problem, they tell me 2 double dot terms. Here's one, the acceleration of c. That's the cable being pulled in at a rate. I can tell it's a double dot term because of the unit second squared. So that's 1, and here's the other one right here. So they're telling me 2 of them. So that means I can find all double dot terms that I want. Has nothing to do with forces, therefore it is not a chapter 13 problem, and so I don't need a free body diagram. Okay, so how do you do it? Well, you're looking for relationships between the motion variables. What I like to do when I'm struggling with one of these things is I like to define positions or variables for everything that moves. And so in this case, I have a position B and a position of Y. The other thing I'm going to do is use an extra one because I'm just trying to make a point here. I'm going to call this XA right there. I don't need this many variables because it's a little bit redundant. Anyway, the other thing I'm going to do is count the number of ropes that I have. I have 1 rope here, and I have another rope right here. And so what I'm going to do when I'm looking for relationships right now, the only thing I know to do is to write down lengths of ropes. So that's what I'm going to do here. So the length of rope number 1 is real simple. It's just XB. So I think that one's fairly simple. The length of rope 2 is 2y because you have a length along here, which is a distance y, plus or minus some constants, but keep in mind I'm going to differentiate it, so I'm not too worried about constants. And then here's another distance right there. And yeah, okay, this is a constant in here, so I'm not going to worry about that. So that's the length of the second rope. So now what you do with that is you differentiate it twice. Now be careful because in this particular case, the acceleration, the change in the lengths are not 0. Because these ropes are actually changing length. So when you get to the double dot, you can put in the correct value. Because the cable at D is being pulled in. The cable is getting smaller, so it has an acceleration which is negative. And same thing here. So the L2 double dot is given, and it's negative because the rope is actually getting smaller. So there's my two equations. Now, if you count the number of unknowns, you have xb double dot and you have y double dot. So you can solve for y double dot and you can solve for xb double dot. Okay. So the next thing is to you're looking for D. So you need a relationship for D, because what I really want to do is I want to find the D double dot, because it's a time spanner. Since I'm interested in D, in the time that D happens and does what, I don't really care about Y, I don't care about XB. What I really want is I want the D. So what I'm going to do is I'm going to do it two ways. One thing that I'm going to do is over here in the red. Okay, I'm going to, and I think this is probably the easiest for people to do. I'm going to walk from the left wall to the right wall, and I'm going to write down an equation. Now the reason I know I can do that is because it's the 2 degree of freedom, and because they give me two double dots, I can find all double dots that anybody wants. I want D double dot. I'm going to try to find D double dot. So here's what I'm going to do. I'm going to start off over here against this wall. So I'm going to start here, and I'm going to walk until I get over to here. Whenever I go to the right, I'm going to say I'm going to walk forward or positive. If I have to turn around and come back, I'm going to be walking a negative. Left would be negative. Okay. So what I'm going to do is I'm going to start it at the wall, and I'm going to walk along the rope until I get over to this point right here. So how far did I walk? Well, that one is right here. I walk positive, I walk to the right, XB. Then what I'm going to do is I want to bring in the variable D. So what I'm going to do is I'm going to, where I'm at now, I'm going to walk backwards until I get to this point. How far did I walk? I walked a distance D. Which way did I walk? I walked left. So I say negative D. Now I'm at this edge. Now I'm going to walk from here until I get over to here. How far is that? That is a distance constant. Which way did I go? To the right, positive. And then I'm going to walk from there until I get to this wall over here. How far? I'm going to walk a distance Y. In what direction? To the right, positive. How far have I walked? Well, I've walked a total of W. We're going to do this a lot when we get into complicated mechanisms and machines and that sort of thing. So we're just going to walk from one place to another, and we're going to write down what we walked. Now what I'm going to do is, just like in a rope, I'm going to differentiate. So X changes, so I have an X double dot, XB double dot. D is changing, so I'm going to differentiate that. CA is a constant, so it ends up being 0 when I differentiate it. And you have a Y double dot. The value W, well, that's a constant as well, so when I differentiate, I get 0. So this is an equation that says, all right, this will relate the D to the other value. So what is XB double dot? Well, from up here, I know that XB double dot is a minus 5. What is Y double dot? Well, Y double dot is a negative 3t squared. So I put those values in, and I solve for D double dot. D double dot ends up being this value right over here. Okay, now another way to get it, since you were asking about relative velocities, is I'm going to use relative velocities. I'm going to try and show you that I get exactly the same thing. Because the D, this distance D, measures between the edge of box A over to box B, D is actually equal to the position of B relative to A, right? Because what D is it is the distance measured, the distance to B measured from A. So that would be the position of B relative to A, which I've shown there. This term right here, XA, that is the position of A relative to the ground. Why? Because it's measured from the ground, from the point on the ground, over to body A. XB is the position of B relative to the ground. Why? Because it's measured from a point that's fixed on the ground to B. So that's those values. So what I'm going to do is I'm going to plug it in. Okay. So so the acceleration of B relative to the ground is xb double dot, which is -5. I got that from the rope equation. If I look at the acceleration of A relative to the ground, that's equal to -y double dot, right? So the acceleration of A measured from the ground is -y double dot. That's a 3t squared, right? So as essentially what's happening is because the rope is being pulled in, body A is moving to the right. So there's my acceleration of A relative to the to the ground. Now the acceleration of B relative to A, and I'm going to build up an equation. B relative to A, I need a subscript B, so I find one right here. So right there, let's see, I'll put it in a different color. I find this guy right here and I plug him in because I need a subscript B, and it's the only one I can see, subscript B. So I have relative to G. Now I got to get rid of the G and get an A. So what I really need is I need to add G relative to A, and this will give me a valid equation because the subscript starts with B and it ends with A, and the intermediate ones are the same, G. Okay, so that's a valid equation, but unfortunately I don't have this term. I don't have this one, but I have the opposite of it. And so if you remember, you can flip these subscripts by changing the plus minus sign in front. So I do that. Okay, so here's the original term that I have, and now what I'm doing is flipping the plus to a negative, and I flip the subscripts. Okay, so several of you realize that the relative velocity is the subtraction of the two. Okay, well that's fine. Now let's just plug in. Okay, what do I have? I have the acceleration of B relative to A, which is D double dot. That's the acceleration of B relative to A. Remember, that's because D is measuring the position of B measured from the edge of A. Right, so that's D double dot, and that equals the acceleration of B relative to G, which is -5, minus the acceleration of A relative to G, which is right here, 3t squared. That's the same formula I had before. So to finish this off, I realize it's a time spanner. I have interest in D. I'm going to integrate this. So the D double dot is D of D dot dt. It's unfortunate that the variable is called D. But anyway, so that's what the double dot is. And so I'm going to take the dt and throw it over to the right-hand side. Separation of variables, that's the only thing I know to do. And when you integrate it, you'll end up with a -5t minus t cubed over 3, which gives me t cubed, plus this arbitrary constant. How do you find the arbitrary constants? Well, you have to know a condition. I know that at time equals 0, it's at rest, so d dot is equal to 0. So you put in 0 for d dot, you put in 0 for t, you find out that c is equal to 0. Now to get the d, I'm going to integrate again. So I'm going to take this, this equation, and I'm going to integrate it one more time. And So when I do, I end up with this term, and I have another arbitrary constant. Don't forget those arbitrary constants. This time I need a condition. Well, the condition is that d is equal to 3 when time equals 0. So I put in 3 for d, I put in 0 for t, I solve for c prime, boom, I get the c prime. So now that I have that, the final equation for d is d equals minus 2.5 t squared minus 1/4 t to the 4th plus 3. And then what you want to do is you want to find the time when d is equal to 0. So you just put in a 0 here, and you end up solving for t. The easiest way to do that, well, besides using Mathematica, would be to realize that this is, we'll put in u instead of t squared, minus 1/4 u squared plus 3. And that's the quadratic formula, which is, you can use the quadratic formula to get u. So you find the u, you get two numbers, right? And then you'll simply say that t is the square root of u. So you can find that value. But the easiest thing to do is punch it into Mathematica. Okay, so that is two different ways to solve this particular problem. It shows some relative motions, and it also shows the use of rope equations. All right.